Good day, students. What we are going to learn today is section 7.2. In this section, we are going to learn about covalent structures. First, a quick recap. Consider the case of your chlorine again. Chlorine, right, based on our previous lesson in 7.1, will form a covalent structure with another chlorine atom that looks something like this. And this is actually your Cl2. Consider a container full of your chlorine gas. This is the container. In the container, there are diatomic molecules of your chlorine molecules. So they look something like this. Now, students, as you can see in this picture here, each of these is a diatomic chlorine molecule. Within the molecule itself, the bond is magnified as such. Is what we call the strong covalent bonds. And this covalent bond occurs within the molecule. Now, how about the forces that exist between the molecules, as represented by these dotted lines that I am actually drawing? Now, this dotted line represents what we call a weak intermolecular forces. And these weak intermolecular forces, they exist between the molecules. Weak intermolecular forces, okay, these forces causes this whole chlorine molecule, hold all these chlorine molecules close to each other, but they are still generally weak. They attract, so that's why, to be more precise, they are called weak intermolecular forces of attraction. Now, so what happens is, when this is a kind of structure that actually is in place, we have within the molecule itself, strong covalent bonds. Between the molecules, it will be weak intermolecular forces of attraction between the molecules. When this kind of structure happens, this is what we call the simple molecular structure. Now, simple molecular structure is just but one of the covalent structures that you guys will learn. When there is simple molecular structure, students, another type that I will be discussing today is the giant molecular structure. I will share with you guys more about this giant molecular structure later, but for now, let us consider the simple molecular structure. Number one, we want to consider the properties, and what happens is the first property you must take note is they are characterized by low melting point and boiling points. Why is this so? During melting and boiling, when there is a change of state, it is actually these weak intermolecular forces of attractions that needs to be overcome. It is not the strong covalent bonds that needs to be broken, because these weak intermolecular forces of attraction are weak. Basically, what they do is they do not require a lot of energy to be broken. So they have a low melting and boiling point because the weak intermolecular forces of attraction do not, require a lot of energy to be overcome. That is the first thing that you want to know. Secondly, we want to know that for this simple molecular structure, right, when we place them, when we place them in water, when we place them in water, right, they are insoluble. Whereas when we place them in organic solvents, such as oil, organic solvents such as your oil, they are, however, soluble. There's one more property that you need to know concerning the simple molecular structure. Well, the molecules in simple molecular structures, right, they do not, they do not conduct electricity. They do not conduct electricity. What is the reason? Now, in order for electricity to be conducted, right, we need either free electrons or free ions. Now, free electrons and free ions simply means that there are electrons and ions that can move about. These free electrons and free ions would then be able to carry so-called the charge of electricity so that the thing can actually conduct electricity. In this case, they do not conduct electricity because they do not have any free electrons or ions in them for the simple molecular structure. Let us now consider your giant molecular structure. Now, a giant molecular structure basically is as such. We want to consider the example of diamond. We all know that diamond is made up of carbon. Consider with me carbon. Okay, carbon is actually in group 4. So it means that it has a valence shell of 4 electrons. Okay, I have 1, 2, 3, and 4. So what happens in the context of carbon is that in order to obtain the stable octet configuration, it will share these electrons with another 4 more carbon. So what happens is the resultant structure looks something like this. So in this case here, there's 1 carbon here. Now, this carbon will have 1 electron shared with another carbon over here. Here, another carbon will share with it. Here, another carbon will share with it. And here, another carbon will share with it. So 1 carbon is bonded to another 4 more surrounding carbons. But in the same way, these carbons will then again share, okay, their electrons with another 4 more surrounding carbons. Now, as you can see, each carbon will be bonded to 4 surrounding carbon, and as a result of this whole sharing and formation of covalent bond will extend throughout the molecule. As a result of this, they will form what we call a giant network of atoms. Okay, they are covalently bonded. The keyword here is a giant network of covalently bonded atoms. So it's as if when you hold 1 diamond, it is 1 giant molecule with all the carbons bonded through a covalent bond. So what happens is, for the case of carbon, if you were to draw it out, it will be such that if I use a circle to represent 1 carbon, I have 1 carbon over here is bonded to 4 more carbons surrounding it. And these 4 more carbons, okay, will then be joined to another 4 more carbons. Okay, and we can continue. So in this case here, this is like this. Okay. So what happens? You form a three-dimensional giant structures that is a network of covalently bonded atoms. So what does this mean in terms of the properties of a giant molecular structure? It simply means that when it comes to a giant molecular structure, I want you now to compare with me the first point over here. Now, let's compare point 1 with point 1 of a simple molecular structure. What happens is, for the giant molecular structure, it will have a high melting point and boiling point. Because in this case here, okay, instead of weak intermolecular forces of attraction being broken, in order for melting and boiling to occur for a giant molecular structure, okay, you actually need to overcome the strong covalent bonds. So it's because that strong covalent bonds, when we say bonds, we usually say broken instead of overcome. So strong covalent bonds need lots, okay, to be precise, large amount of energy, okay, large amount of energy to be broken. And let's consider another point. In this case here, for the case of your giant molecular structure, now, okay, it does not dissolve in water. It is insoluble in water. And when it comes to organic solvents, okay, it is also insoluble. So there is one difference, okay, it has between the solubility of your simple molecular structure and giant molecular structure. Okay, for the case of a giant molecular structure, it also does not dissolve in the organic solvent. In a giant molecular structure, what happens is, okay, it also do not conduct electricity as well. And the reason is the same. As you can see, each carbon, okay, recall, okay, all the carbons will have their electrons covalently bonded. So as a result, they do not have any free electrons or free moving ions to conduct the electricity. So as a result of this, there is no way that your giant molecular structure can conduct electricity as well. So with this, these are the two molecular structures that are covalent structures. And now, before we end this video, I want to show you three structures, okay? Three giant molecular structure. Hi students, now let us come back to the three giant molecular structures that you need to understand for your O-levels. Let us first consider the case of your graphite. Now students, in graphite case, right, as you can see, I've actually drawn two layers of graphite. Between the layers, the carbon atoms are bonded by strong covalent bond. one carbon is covalently bonded to 3 other carbons. Students, if you recall, when this is actually the case here, that means your carbon looks something like this. I have one carbon here, covalently bonded to 3 more carbons. This means, if you recall, carbon has 4 electrons. If it is only bonded to 3 carbon, that means each carbon will have one free electron left. This one free electron, students, can be free electron, okay? This free electron can actually be delocalized. The keyword is delocalized. And when this delocalization occurs, this electron becomes something that can carry charges, and therefore, okay, for graphite, it will be able to conduct electricity. But however, students, this electron can only be delocalized across the layer, which means you can only conduct electricity when they are putting it in such a way that electricity can flow only along the layers. Now, so what happens is that because each carbon is bonded to another 3 more carbons, what they will form is essentially a continuous hexagonal layer. And what happens is, this is along the layers, okay? But however, when it is between the layers, however, these are actually the weak intermolecular forces of attraction. Now, because these are weak intermolecular forces of attraction, that means basically, right, okay, between the layers, okay, it is actually soft and it is slippery because the layers can actually slide over each other. So, okay, between the layers, okay, to be more precise, weak intermolecular forces of attraction holds the layers, okay, together. And as a result of this, the layers can slide, okay, can slide over each other when a force is applied. So which means if I apply a force, this layer can actually glide over each other. So that's the result of this. You can see that this line, spots to spots, the spot on the first layer, the carbon on the first layer, is not exactly aligned directly to the carbon on the second layer. So as a result of this, okay, graphite, not only can graphite slide, but because of the free electron that has delocalized the layer across the layer, along the layers, okay, along the layers only. You can actually conduct electricity if they are placed in the right way to conduct electricity along the layer. Now, let's take a look at your diamond and your silicon. Now, unlike your graphite, the diamond, right, have one carbon bonded to 3 other carbons. So as a result of this, it forms what we call a 3-dimensional structure, all held together by covalent bonds. So what happens is that large amount of energy is required, okay, to break, okay, these strong covalent bonds. So, which basically means that in this case here, you would have a high melting point and boiling point as well. Next, as you can see, your diamonds, the carbon electrons, there are no free electrons because every carbon's electrons here has been used to form covalent bonds. So as a result of this, they do not conduct electricity because there are no free electrons. Okay, there are no free electrons in there. So, and because of the fact that it has a 3-dimensional structure and strong covalent bonds, this whole structure becomes hard. Hard as a result of the 3-dimensional structure it has, as well as the strong covalent bonds that requires large amount of energy to break. Silicon, students, is pretty much the same. As you can see, the only difference is in this case here, every oxygen, okay, this dot here, okay, is oxygen, okay, whereas the shaded spot is silicon. So what happens in this case here is that every silicon, okay, is bonded to 2 other oxygen atom, and every oxygen atom, right, okay, every silicon is bonded, okay, sorry about that, every silicon here is actually bonded to 4, okay, 4 oxygen atom. 4 oxygen atoms, and every oxygen atom, okay, is actually bonded to 2 silicon atoms. So what happens is, as you can see, similar like diamond, it forms a 3-dimensional structure, and these bonds are also covalent bonds. This means that it is going to be hard. It will have, because you need large amount of energy to break the covalent bonds, it will lead to it having a large melting point and boiling point. And similarly, like diamond, this structure here has no free electrons, so it will not be able to conduct electricity. Just like your diamond will also not, okay, be able to conduct electricity. Now, students, one more thing. In this case here, similarly, for graphite, right, what happens is something that I forget to mention just now, is that your graphite too have a high melting point and boiling point, because Although it has weak intermolecular forces of attraction, during melting and boiling, we actually need to break these strong covalent bonds, okay? During your boiling and your melting. So as a result of this, your graphite, similarly like your diamond and your silicon, will have a high melting and boiling point. And this is your section point 2. Thank you.